check this out. I'm going to show you how I afforded this car. Okay, you ready? All right, $118 for car insurance. That's how much I was paying, okay? I picked up
a much more probable path for how it... The game Wordle has gone pretty viral in the last month or two, and never one to overlook an opportunity for a math lesson. It occurs to me that this game makes for a very good central example in a lesson about information theory, and in particular a topic known as entropy. You see, like a lot of people, I got kind of sucked into the puzzle, and like a lot of programmers, I also got sucked into trying to write an algorithm that would play the game as optimally as it could. And what I thought I'd do here is just talk through with you some of my process in that and explain some of the math that went into it, since the whole algorithm centers on this idea of entropy. First things first, in case you haven't heard of it, what is Wordle? And to kill two birds with one stone here while we go through the rules of the game, let me also preview where we're going with this, which is to develop a little algorithm that will basically play the game for us. So I haven't done today's Wordle, this is February 4th, and we'll see how the bot does. The goal of Wordle is to guess a mystery 5-letter word, and you're given 6 different chances to guess. For example, my Wordle bot suggests that I start with the guess crane. Each time that you make a guess, you get some information about how close your guess is to the true answer. Here the gray box is telling me there's no C in the actual answer. The yellow box is telling me there is an R, but it's not in that position. The green box is telling me that the secret word does have an A and it's in the 3rd position. And then there's no N and there's no E. So let me just go in and tell the Wordlebot that information. We started with crane, we got gray, yellow, green, gray, gray. Don't worry about all the data that it's showing right now, I'll explain that in due time. But its top suggestion for our second pick is shtick. And your guess does have to be an actual 5-letter word, but as you'll see, it's pretty liberal with what it will actually let you guess. In this case, we try shtick. And all right, things are looking pretty good. We hit the S and the H, so we know the first 3 letters. We know that there's an R. And so it's going to be like SHA something R or SHAR something. And it looks like the Wordlebot knows that it's down to just 2 possibilities, either shard or sharp. It's kind of a toss-up between them at this point, so I guess probably just because it's alphabetical, it goes with shard, which, hooray, is the actual answer. So we got it in 3. If you're wondering if that's any good, the way I heard one person phrase it is that with Wordle, 4 is par and 3 is birdie, which I think is a pretty apt analogy. You have to be consistently on your game to be getting 4, but it's certainly not crazy. But when you get it in 3, it just feels great. So if you're down for it, what I'd like to do here is just talk through my thought process from the beginning for how I approach the Wordlebot. And like I said, really it's an excuse for an information theory lesson. The main goal is to explain what is information and what is entropy. My first thought in approaching this was to take a look at the relative frequencies of different letters in the English language. So I thought, okay, is there an opening guess or an opening pair of guesses that hits a lot of these most frequent letters? And one that I was pretty fond of was doing other followed by nails. The thought is that if you hit a letter, you get a green or a yellow. That always feels good. It feels like you're getting information. But in these cases, even if you don't hit and you always get grays, that's still giving you a lot of information since it's pretty...
Say, interesting. The probability of A given B. This is information. How much information? Basically kind of goes from A given B. So if before the probability of what? An event. It's all uniform, I guess. These are all the possible outcomes. Maybe you get some piece of information here and you rule out, this possibility. But you still have, all this is still possible. All these outcomes are still possible. But if you get a lot of information, if you get a lot of information, maybe it would cancel out, you know, all these guys, just leaving you with like these two right here. Like that's a lot of information. That's pretty dang intuitive. So your new probability space basically looks like, you know, basically looks like 50-50. Or maybe your whole, you know, thing had like all these whatever, but it kind of narrows it down to this right here, just these two guys. So now your sort of sample space looks like, you know, it's basically like this. These are the only two possibilities left. These are the only two outcomes left. Okay, so yeah, you have a lot of outcomes here. And then maybe you get a lot of information and there's still some uncertainty. You don't know 100%, but this guy's like 95% and this guy's 5%. Like that's a lot of information. So the amount of information is related to, I guess, like the number of outcomes remaining, and also like the distribution of those outcomes. But yeah, I like this though. This whole thing, like A given B, like this is the information. How much information?
There's the word that doesn't have any of these letters. But even still, that doesn't feel super systematic because, for example, it does nothing to consider the order of the letters. Why type nails when I could type snail? Is it better to have that S at the end? I'm not really sure. Now, a friend of mine said that.
All right. I'm out, y'all. Peace.